Hi class, welcome to the second part of today's lecture. So this half of the lecture we're going to talk about the Earth's climate and in particular the fact that it is changing. This is the part of the course where this all overlaps very well, and I think it's important for all of you to hear a little bit about the climate science as we go along. Your book talks about this in the chapters that we're reading right now, so there will be some additional resources for you there. Okay, so in the background behind me is a picture from Antarctica of an iceberg that has grounded itself near the coast. I'm showing you this because we're going to talk about ice in Antarctica, and it's part of the climatic record that we refer to. So in particular here, you can see the fine layers in the iceberg. Okay, and then you'll notice the deep blue color as well. Okay, so the fine layers are just year after year after year after year of snowfall falling and then compressing, and the deep blue is evidence of the amount of compression that this ice has undergone over time. When the ice in Antarctica gets compressed, it's very dense and it's very pure. And so you get that kind of deep blue, what we call glacier blue color. Now this is actually a really enormous structure here. So you can see this little piece of ice down here at the bottom. If you were riding by this iceberg in a zodiac, you'd be about half the height of that piece of ice that you see right there. Okay, so this is an enormous structure, but you can see those layers. And when you go to Antarctica, you see these layers, and all the ice you see there, you see this deep blue color because this is the ice that's coming off the edge of the continent all the time. Okay? Okay, so we're going to talk about climate change. So this is a version of a talk that I usually do for my science classes. So it's been reduced in length because we're not going to talk about everything I normally talk about when I do talk about climate. But it's going to talk on the high points. So we're going to talk about the evidence that we have for the climate change. In particular, we're going to talk about the temperature data and about the carbon data because that is relevant to our discussion of exoplanets, but it's actually the primary data that we have for the changes that we see on Earth. We are going to not talk about all the global effects that we see. We won't talk about, shifting climatic patterns on small scales. We won't talk about shifting in farmlands. We won't talk about global sea level rise. We can certainly talk about all those things. I will give you references that you can go read about those things. And I'm certainly happy to talk about any of those things if you want to afterwards. Okay, so why are we talking about this? So the point is that climate plays a huge role in the habitability discussion of planets. And just in our own solar system, if you look at Venus, Earth, and Mars, they all are in principle near or in the habitable zone, but they all show very dramatic differences in what their surface conditions are like. And the question is why, and how does a planet get into that state? And I think both Venus and Mars are warnings about how fragile balanced climate actually can be. And we look at Venus and Mars a lot when we study climate science, mostly because we can use our models for climate, the computer simulations, the theories that we're using to describe the evolution of the hydrosphere and the temperature. All of those models correctly predict the conditions we see on Venus. They correctly predict the conditions we see on Mars, and that's one of the things that lends confidence that they're telling us accurately what we can expect to happen on Earth. Okay, as we'll discuss, and as we have discussed, climate change on the planet is one way for life to exterminate itself. So you'll remember early on we talked about how the advent of cyanobacteria changed the Earth's early atmosphere from a carbon dioxide rich atmosphere. The cyanobacteria are photosynthetic, changing it to an oxygen rich atmosphere. That completely changed the Earth's climate, and it drove some life forms to extinction, but it enabled other life forms to survive as well. We'll return to this in week 9 in the context that we're talking about climate today. If a species tips its climate severely or dramatically and disrupts its ecosystem, what can happen to the world. The other reason to talk about this is that for many of you, this is going to be one of the few science classes that you take during your college career. And so as a consequence, when you go out into the world and you are a citizen and you are leading your life and doing the job that you do, you are still going to have to think about science and the implications about what science is telling you about your life and your future and your children's lives and your children's futures. Climate change is the singular most important scientific crisis facing the world. It's the one that science has the most to say about, both in terms of what's going on, what can happen, and what we should be doing about it. And your generation is going to be the first generation of people to see really serious changes that dramatically change the way our civilization operates on this world. And so as a consequence of that, you have to be well-versed enough and comfortable enough talking about science and hearing science information coming to you such that you can make informed decisions, such that you can go out and get more information and educate yourself about what the science is really telling you, so that you as a citizen, as a global citizen, as a citizen of whatever country you belong to, you can make informed decisions based on rational thinking and based on evidence that you think. I'm sure, as most of you know, climate, particularly here in the United States, has become a very politicized topic, and it shouldn't be that way because it's very clear what the evidence is telling us. It's very clear what the observations are. It's very clear what the boundaries of what we understand and what we don't understand actually are. Okay, and it's important for you as a citizen to have some notion of what that is and have some ability to discern what data is trustworthy and not trustworthy. Okay, so that's why we talk about it in this class. Now, if you and I were in class together, when I talk about this, usually what I do is I solicit from you things that you've heard about climate change. And sometimes I'll ask you just to tell me things that you know are happening, things you've heard is happening. I'll ask you about things that you really don't understand or that you're confused about, things that you've heard people debating about, okay? Now, since we're not together, I can't do that, but I have the record from the last time I taught this class. And these are the sorts of things that, that all of us have heard and that usually get called out. So I usually seed the discussion with the first one there, which is we've all heard that polar bears are doomed because of the changing conditions in the Arctic. There are very dramatic examples of this. I've been to Churchill on polar bear expedition, and the polar bears are creatures that live on the pack ice. And if the pack ice is going to disappear, then that's dramatically going to affect the lives of the bears. There's a whole long list of things that you've heard. Glaciers are disappearing. That's certainly happening. We've seen places where glaciers have completely disappeared. Severe weather is getting worse because of climate. Sea levels are rising slowly, but they will accelerate. Farming zones are changing. Many of you have heard we can't do anything to stop this. Many of you have heard that we can, and we could stop it if we just start now. Many of you know that this is tied up to the energy consumption of our civilization, so renewable energy is a part of this. Many of you know that Earth was warm in the past, and you've heard the arguments that this is just part of the natural cycle, and that humans aren't part of this. And most of you, I'm sure, know that humans certainly are part of this, that this is anthropogenic, as we say, in origin. Okay, so this list could go on. There's lots of things all of us have heard about, and so let's talk about just a couple of these things. We could have an entire course and an entire semester talking about climate. We obviously can't do that, but we're going to spend just this half hour here together talking about it. So understanding climate, there's basically three parts that scientists lean on. There's the data, there's the modeling of the climate, and then there's the interpretation. And the data is what it is. It's very robust. We have many lines of data that all agree with each other. And this is really the reason scientists are very confident and in consensus, as we say, that the climate is in fact changing. The modeling, as I discussed a moment ago, is largely computer-based because the climate is a very complicated system. You can do very fundamental calculations by hand. Many of those were done in the 18th and 19th century, and they accurately predicted what is happening as a result of fossil fuel emission in particular. And then the interpretation is really the hard thing, because interpretation is done not not because we necessarily need to know what's going to happen, but because the changes that happen are going to influence our society. And that's where most of the conflict happens, right? We interpret the fact that a particular localized climate on the continent is going to become hotter or drier, and that's going to change farming in that area of the country. Well, that has implications for the people who already live there and make their lives farming. And so that's why there's so much strife and argument about climate. Is I think it's largely around this point, around the interpretation, because that's what directly impacts people's lives. Without fail, this is one of the hardest problems in science today. And for many reasons. The science itself is complex. We're getting better at it. We understand the fundamentals, but all the nuances are hard. And the nuances are what people argue about. But the global picture is very accurate and well known. But it's hard because it's not just science. We can't, the way you and I are talking about exoplanets and climate on exoplanets, we can't just talk about it like it's not going to impact us. You and I can talk about exoplanets till we're blue in the face, and it's not really going to affect whether or not I can get up in the morning and go to work and go to school and what I'm going to do for my summer vacation and so on, okay? But climate, the discussions do have impact on us. So there's politics wrapped up on this, and there's economics wrapped up in this. And then I'm sure those of you who pay attention to this, you know here in the United States, that's what most of the arguing is about. The data itself is very complex, and there's a lot of nonlinearity. We'll talk about what that means in a minute. And so I think from that perspective, we are getting better. We have been limited, especially when I first started doing this, when I was an undergraduate, by the simple fact that we just didn't have the computing power, the capacity to deal with the data and deal with the simulations. That is getting better. Supercomputers today are dramatically faster, dramatically bigger, and can do amazing things. And so the picture is becoming clearer, and we're beginning to understand more about what's going on. Okay, so I'll remind you we can't cover everything, and we're just going to focus on the temperature record and the CO2 record. Okay, so let's talk about the data. So let me show you some data for the temperature record that's in the form of a movie. So the way we normally express the trends in temperature is we describe something called the temperature anomaly. And what the temperature anomaly is we define what the baseline average is from some set of data. And then the anomaly is whether or not the data in any given year, or whether or not the data averaged over a couple of years, is different than the average that we set at the beginning. Okay, so it can be different by being lower or colder. It can be different by being warmer. Okay, and the point here in the data I'm about to show you is that it doesn't matter what we set the baseline, the sea level of temperature, if you will, was. The temperature is dramatically changing from cooler in the past to warmer in the present day, and as we expect, warmer in the distant future as well. Okay, so here's a movie of the 5-year global average. So the global average is taken in the early 1900s, and the data goes back to the late 1800s, okay? And then this movie will slowly change over time, okay? So white is at the global average that we expect. Yellow and red are above the global average. That is, we say it's anomalously high, and then dark blue is colder than the global average. It's anomalously low, okay? So I'll let the movie play there. You'll see the years spooling by there on the bottom. You'll see compared to the mid-1950s, the 1800s were cooler than they are now. As we approach the middle of the 20th century, we get to the global average. The planet's mostly white. And then as we go past the 1950s, where we took the global average, we see the planet getting more and more yellow and more red. You'll see that's happening all over. And in particular, I'll draw your attention to the Arctic and the Antarctic. That has dramatic consequences for the global temperature of the planet. Okay? So this is the record of the planet's temperature. It is composited from temperature data that we have from all over the planet. We don't have complete temperature data, so you look at the topography, you look at the adjacent data between different thermometers, you look at what models may predict, but you can fill in the data all over. So People have always been a little leery of this, and so there was a big effort called the Berkeley Earth Surface Temperature Project about 10 years ago. So that's called BEST. If you are reading about climate, you'll hear about BEST. And if you go to berkeleyearth.org, you can see what they did to validate this data. They did their own independent analysis. They included all the uncertainty in thermometers. They included the fact that the thermometers are unevenly spaced, all sorts of stuff. And they arrive at the same conclusion that we just showed you. The planet's temperature is warming, and it is getting warmer by the moment. Those of you who are interested in this, there are lots of citizen science projects that surround climate. So in particular, I'll point you to one called Old Weather. So this is through Zooniverse, which is a big citizen science project run out of the Adler Planetarium here in Chicago. So if you go to oldweather.org, or if you go to zooniverse.org, you can find the Old Weather link there. This is looking at old temperature data that's been recorded by ships crossing the oceans on global shipping routes, and then incorporating that into the scientific databases so that we can make pictures like this more accurate. Okay? Now here's a slightly different movie showing the average. So these circles, so this is by month. So rather than averaging years together, we take the averages in any given month and we ask, are February's hotter than normal, or are March is getting hotter than normal? What you'll see is every month of the year is getting hotter than normal, okay? So if the temperature is there at 0 degrees, that's the global average that we set. And then if the temperature is colder, it'll be inside that circle. And if the temperature is warmer, it will grow outward. You'll see two marks there, 1.5 and 2.0 degrees centigrade. Those are key marks that we in climate science, when we pay attention to this, regard as barriers that we don't want to cross, okay? Because they will have dramatic consequences for the climate overall, okay? So let me play this movie. You'll see it is a spiraling outward, okay, by year there. Okay, so it's going around in a circle month after month after month, okay, and you'll see it's kind of right there around those global averages right now. But over time, as we accelerate through the middle of the 20th century and into the 2000s, it is certainly growing, okay? And so today, we are very near that 1.5 degree shift that climate scientists are so worried about, okay? So the temperature is definitely warming on the planet, and the question is why? Okay, now we think it is due to anthropogenic emission of greenhouse gases. We know exactly what the effect of greenhouse gases is. We can test it in the laboratory. You can do experiments on your back deck with carbon dioxide and show that carbon dioxide is an effective greenhouse gas. We see it on the planets around us. We see the runaway greenhouse effect on Venus due to the excessive carbon dioxide. And so we can ask what is happening to the carbon content of the atmosphere on Earth, and thus predict what that's going to do to the global temperature. What you see here is a record of the carbon dioxide concentration on the planet. Okay, so the current level is marked there today on the extreme right. You'll notice it's up around a number called 400. So this is in parts per million. If I take 1 million atoms out of the atmosphere and I count how many of them are carbon dioxide, this is how many are carbon dioxide for every 1 million atoms that I take. Okay, so right now we're actually more than this, but the time this graph was made, we were at 400 parts per million. In 1950, we were substantially lower. We were down around 320 parts per million. Okay, and if you go back in time through the geologic record, we'll talk about how we measure this, you can see that the carbon dioxide level was always substantially lower than the levels that we see now, and substantially lower than the averages we saw in the middle of the 20th century. Okay, so the historical max is somewhere around 300 parts per million, and you can see that in the geologic record for centuries, going back, that's 400,000 years there, we never saw it cross that 300 parts per million level. Okay, so what's happening over here on the extreme right is humans are starting to consume carbon in mass quantities in the form of fossil fuels. We started burning coal, we started burning oil, we started burning gasoline. And the byproduct of combustion of fossil fuels is carbon dioxide and carbon monoxide and methane and all kinds of other greenhouse gases that are a result of the industrial production that we do on this planet today. Okay, so today I looked it up. The April 2020 number average is 415 parts per million. So even based on when this graph was made in 2016, the number is still increasing, and it is not expected to abate. There are certainly changes going on right now because we're all locked up at home as a result of the global pandemic. That is a very interesting data point for us as scientists to look at, to ask, what does civilization have to do to change its carbon output? But in terms of what we see in the atmosphere, what we call the carbon loading, it will take time for that to settle out and change. And so just being locked up at home for a little while isn't going to change the trend in this graph. If we go back to business as normal, we continue driving, we can continue burning coal, we do all the things that we do, okay? So why all the fuss about carbon? So you see here in the top, that's a typical chemistry model for a carbon dioxide atom that you might see. Those of you who have built stick models in chemistry know this. So this shows why certain molecules are very good as greenhouse gases. It has to do with the fact that these bonds here can absorb energy, but they don't break. Okay, so that carbon dioxide molecule is very good at absorbing energy because those bonds can twist, they can vibrate, they can bend. It has many ways for that molecule to absorb energy from the environment around it. And because it can store that energy, it stops the energy from going to outer space. Okay, eventually it gets rid of the energy, but as we discussed last half of the lecture, when it gets rid of the energy, some of the energy gets released outward. That's the energy that would have gotten released outward if the greenhouse gas wasn't there, and some of the energy gets released downward, and that's the retained energy that's causing the planet to warm. Okay, so there are lots of different greenhouse gases. I've shown their molecular models down here, and they all have similar ways that they can store energy, just like this carbon dioxide molecule that I showed you here at the top. Okay, so CO2 is just one greenhouse gas produced by our civilization. We are producing it in massive quantities. If you look at all the greenhouse gases that humans emit, the breakdown is over here in red. About 72% of all the greenhouse gases we emit are carbon dioxide, which is why you hear us talk about carbon dioxide all the time. There is about 18% of it's methane, and about 9% of it is nitrous oxide. Okay, all of these greenhouse gases cause the Earth to retain heat more effectively by this greenhouse effect. Okay, and we talked about this last half of the lecture. This is a slightly different graphic, I promised you, showing the same thing. The energy from the sun comes in through the atmosphere and strikes the surface. Some of that's reflected, some of it's absorbed by the surface. The energy that's absorbed by the surface is re-radiated into the atmosphere where the greenhouse gases absorb it. And then when they radiate the energy, some of it goes to space and some of it goes back to the Earth. This is an example of what I told you last class that I don't like about these some of these diagrams, is they don't show the fact that those molecules are still releasing some of the energy to space. The fact is they're releasing some to space and some back to Earth. Okay, and that's what the greenhouse effect is all about. What we're worried about on Earth is that as the greenhouse gases build up, this effect is going to become stronger. And just like we talked about Venus, when the effect becomes stronger, that causes some of these processes to accelerate, which causes it to become warmer. Okay, so that's what global warming and climate change is all about. So how do we know this? Well, we have really good data, and we have data on many fronts that describe what's going on, and they all tell the same story. But the most reliable data comes from what are called ice cores. So the temperature record and the atmospheric greenhouse gas record is stored in the geologic record, and the easiest way for us to get to it is through the ice cores. Okay, so the two most famous cores that we've taken are taken from Antarctica. There are also cores that have been taken from the Greenland ice sheet. The longest core taken is the Epica core. That's taken in an area on Antarctica called Dome C. And then the second longest core is called the Vostok core. That's taken near the Vostok station over Lake Vostok in Antarctica. Those two sites are about 500 or 600 kilometers apart from each other on Antarctica. The Epica core is the longest core. It goes back in time 740,000 years. We count those layers that we were talking about when we look at the Antarctic ice, as we showed in that glacier behind me there when we started class. So the Epica core goes back 740,000 years, which is through 8 glacial ages, through 8 ice ages of Earth. Okay, so this is what lends us confidence that this is not just a natural coming out of ice age, which is something that you often hear people say. The Vostok core similarly goes back 420,000 years and goes through 4 glacial ages. Okay, now the thing about the ice cores, and so here you can see how big they are. Okay, so this is the Vostok team with their cores when they pulled them out, is that the ice is very compactified and very dense. And just like when you make ice cubes in your freezer, if you pull one out and you look at it, you'll see there are little tiny air bubbles trapped in the ice. Okay, well, there are little tiny air bubbles that are trapped in the Antarctic ice and in the Greenland ice, and they've been trapped there since they were put there hundreds of thousands of years ago. They are in their pristine condition from when they were trapped. Okay, so the chemical content of the atmosphere, in particular, how much greenhouse gases were stored in the atmosphere, is preserved in those tiny ice bubbles in the ice core. Okay, so so this is an example, shows you. So the core is about 2.2 miles long. Okay, and they're drilled down through the ice, and then they pull them back up, and you get those cores there that the team was standing there with. Okay, the cores are stored in cold laboratories so that they stay, and then they take samples directly from the cores and drill into them and get the air bubbles out. Here's a close-up picture of one of these cores. Okay, and so if you look, all of that speckle that you can see in the surface of the ice there, those are actually air pockets deep down in the ice that are maintained. The striations that you can see, that is the layering of the ice, okay? Year after year after year, snowfall getting compressed into ice and compressing itself into the Antarctic ice sheet that's been there for hundreds of thousands of years, okay? We know how the temperature goes by measuring the thickness of those layers, because the overall temperature affects the snowfall and it affects the snow melt, which is part of the compression of the ice into the layers. Okay? Now, what we're worried about with climate is we can look at the CO2 in the past, and we know that it was less than it is today. And what we see today is we are pressing the CO2 level up to very high levels that the planet has never seen before. Okay? And what we're worried about is what we call nonlinearity. So nonlinearity means small changes in conditions. I change the CO2 level by some small amount, 10 parts per million, 20 parts per million, and that will produce big and sudden changes overall in the environment. Okay? So normally everything behaves linearly or slowly. Okay? Now you're used to this. So you put some ice in in a glass of water, and you just let it sit there. The water rapidly cools when you put the ice in it, okay? But over time, the cooling slows down, okay? Because the water has come to equilibrium with the environment around it, and then it slowly cools and slowly cools and slowly cools. Nothing dramatic or sudden happens, okay? In climate, we're worried about the opposite kind of that slow, steady evolution. We're worried about very sudden changes that cause the climate to respond dramatically and drastically, diverging very rapidly from that equilibrium where you see slow, steady changes. Okay, so the way I normally explain that to people is to imagine a tower of blocks. So this is my daughter when she was probably about 2, and this was one of her favorite games, was seeing how many blocks she could stack up. Okay, and I don't have my blocks here. They're trapped in my office at Northwestern, but I have a set of climate blocks that I use just for this, and if we were in class, we would do this. We would set a block down, okay, and you can set another block on top of that one and be pretty confident that you can set it there stably, okay? You can set another one on and still be confident it's stable, okay? And you just keep stacking blocks on top of it. Now, the blocks are very stable when the tower is low. I can push a block sideways just a little bit and it's still going to stay a tower, okay? That's the equilibrium condition. The small changes don't change the system dramatically, okay? But as the tower gets taller, things become really nonlinear, okay? And the thing that's becoming nonlinear is the tower's balance. Those of you who are playing Jenga right now while you're locked up in pandemic know this, is that balance is a very touchy thing when your tower gets tall. Small changes in where you place a block at the top dramatically affect the overall balance of the tower, okay? And eventually, you will put enough blocks up that when you put the final block on, the balance shifts non-linearly with a sudden change, and the whole system diverges. In the case of blocks, the tower collapses. And so what we're worried is that we keep piling carbon dioxide into the atmosphere, and small changes will eventually cause the climate to make a sudden shift. It will suddenly get a lot warmer, and when it gets a lot warmer, that has effects on the ocean, puts water vapor in the air. Water vapor is a greenhouse gas that would cause it to warm up. That's the way Venus got ahead of itself, okay? So these are the sorts of things we're worried about with the climate, okay? And it's all about this gigantic feedback system, okay? The temperature rises, that causes things to happen. One example of something that it causes to happen is it's melting the Arctic sea ice, okay? So that's bad because the sea ice is part of the ecosystem there, but it's bad in terms of climate because when the ice melts, it exposes the ocean. And ice is normally reflective, but the ocean is not. The ocean absorbs heat. And so the absorption of heat by the ocean causes the temperature to rise. And that melts more ice, which heats the ocean, which causes the temperature. So this is that kind of feedback loop. So we're worried about dramatic amounts of ice disappearing because it could drive a loop like this. And there's many examples of this kind of feedback loop in the climate system. This is just one, but there are many examples, which is why it's such a complex problem and why there are many places where we can make improvements that can be dramatically important. Okay? So the point here is this is really a serious issue. And we know it's a serious issue. We know what the trends are. We know what's happening. But we don't know all the answers about what to do and about what's going to happen 10 years from now or 20 years from now. We absolutely know what's going to happen on 50 and 100-year timescales if we keep doing what we're doing, because the planet is already heading in that direction. We already see things going on that we can accurately predict, okay? The main issue with doing something about it are political and consumer hangups, which are tied to questions about economics and weighing interests about what our current life is like, about what the current economy is like, about what the current world political and civilized structure is like, and what we would have to do to those systems and how it would change them. And what we're weighing, perhaps not enough, is whether or not those changes are doable and whether or not they're harder than the grim future we might face if the climate were to shift dramatically and in unexpected ways, okay? So the most important thing, as I said at the beginning, is for each of you to become a well-educated citizen. Some of you are going to go into science. That's great. I implore you to think about science related to climate. I'm an astrophysicist, but I try and spend a little bit of my time thinking about this because I think it's important. Some of you are going to become teachers. It's important that you become educated so you can talk to your own students about this. Some of you are going to become politicians. It's really important that you become educated about this and learn how to talk to scientists and understand what they're telling you. But this is the issue of the age, and all of us need to be well-versed and well aware of what's going on, okay? So that's all I'm going to say about it. I will leave you with some resources. These are probably the two best sites to go get authentic information from scientists. So NASA has a very strong climate program, as does the National Oceanographic and Atmospheric Administration, NOAA. NOAA has the National Weather Service and the National Hurricane Center, all those people. So they also have a very good climate site as well. The Pentagon is very worried about this. Those of you who think about military issues and know about the military, if the military is worried about this as a threat to national security, then very likely it is. I've put that link in red because the Pentagon's report about that has disappeared. The current administration of the United States is erasing government sites about climate. And so that Pentagon report certainly is archived somewhere on the web, and I can't find it right now. But when I do find it, I will post a link to it for you to find. And those of you who are people of faith, this is an example of how our religious communities are responding. This is a link to one of Pope Francis's edicts about climate change that he wrote just a couple of years ago. And that's also good reading for people. If you want a good book, then I think the best book that I recommend is this one here shown on the left. This is a book called Dire Predictions, and when I stop the video here, I have my copy here. I'll show you what the inside looks like. I think it's really a great book because it talks about all the data, and then it also talks about all the arguments that people have about climate, and it tells you why we think those arguments are valid or not valid. And so it's really a good book. It's written in, I think, really straightforward language, so it's easy for people to understand even if you're not a scientist, and it has really great graphics. So if you're a person who debates this with your friends and your family, this is a good resource for you if you want to use that to help you. It's a great resource for any of you who want to learn more about this as well. And then lastly but not least, I implore you to listen to scientists who are good communicators about this. So I've listed 4 across the bottom here that I do follow. Michael Mann is very famous. He's one of the authors on this Dire Predictions book. He's a climate scientist at Penn State who's been at this for a long, long time. Catherine Hayhoe, she has a really great YouTube series called Global Weirding. And so she's a climate scientist at Texas Tech. Heidi Cullen is also a good science communicator. She's been at this for a long, long time and is a professional climate scientist who works on climate modeling, as is Gavin Schmidt over here, who is also very good at the public sphere. All of these people appear on social media, and you can follow them and get a lot of good insight from them about this. Okay, so that's all I'm going to say about climate. Before I go, let me show you my copy. This is the first edition of Dire Predictions. My second edition copy is in my office at Northwestern. But the book is very nicely laid out inside. It's all very heavy and friendly in graphics. There is very easy to read text, okay, that describes all of the issues related to science. And so here's an example about carbon cycle. Okay, so I think it's really a nice book. It's easy to read. It's paperback, so it's not too expensive. It's put out by DK, which is a company that I like quite a lot. And so it's probably the best resource, I think, for anyone who wants to spend time thinking about this and learn more about it. Okay, so that's all I'm going to say about this. There is a good section of the current chapters in your book that we're reading about climate change on Earth, so definitely read those. And if you have questions or you want to chat more about this, I'm certainly happy to talk more. Okay, so I hope you're all doing well. Take care of yourselves, and I'll see you next week.